Okay, so hopefully you're liking random variables so far, and I have some very sad news that this will bring us to our last random variable topics for Unit 4, and that is the geometric distribution. And this was actually added into the AP Stats CED back in the fall of 2019, so it's still a relatively new official point or topic in the content. However, you might be very familiar with this distribution because it will remind us of independent successive events, which we talked about in the first half of our probability unit. So, in a binomial setting, the number of trials n is fixed, and the binomial random variable x counts those numbers of successes. In other situations, though, the goal is to repeat a chance behavior until a success occurs. These situations are called geometric settings. So geometric settings will go here. And I don't know why, but in my head, binomial's blue and geometric's green. I'm sorry, I don't make the rules. These settings arise when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability p of success must be the same. In geometric settings, we define the random variable y to be the number of trials needed to get the first success. Thus, y is called a geometric random variable. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p, which is the probability of success on any trial. And thus we see the possible values of y would be 1, 2, 3, all the way up to n. And now notice in our binomial setting, we started off at 0. But here, since we are looking at successes or trials, even if you get a failure on the first attempt, that counts as your first trial. So notice that binomial random variables start at 0 and geometric random variables start at 1. So let's take a look here. There are some conditions of a geometric distribution, and they are fairly similar to that of a binomial. For example, the possible outcomes of each trial can be defined as success or failure. Well, we learned that that would be a binary outcome. Also, knowing the result of one trial does not tell us anything about the result of any other trial. That would be independent. We also look at the number of trials until a success occurs. So this one is a weird one. So we're just going to call this one the trial condition. So we'll call this one trials. Some people call it the first success condition. So it's either bit or biff. And then lastly, there's the same probability p success on each trial. That's our success condition. And so in a binomial setting, we know the number, right? It's a fixed number of trials. And here in a geometric setting, we're just doing some chance process until a success occurs. So this is the bits or biffs. And since the conditions are met, we say that y is distributed geometrically with parameter p, or the characteristic p. So y has a geometric distribution with probability of success p. That's what this small little statement means if these four conditions are met. So that is a little bit of an introduction to our geometric random variable. So let's take a look here at some parameters of a geometric distribution. If y has a geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, up to k. If k is any one of these values, then we have the following output function. We say the probability that y equals k is equivalent to this function. We will take the complements, and we'll do k minus 1, and we'll multiply it by the product. Because this is saying if the first success occurs on trial k, then that means the number of trials before k were all failures, and then we've multiplied by the final success. And again, this is the same thing as independent successive events, so this might feel very familiar to us. We just multiply the complements, and then we multiply the success. And here, there's no combinations because there's not different ways for these events to occur. Either it's a success or it's a failure, and because of this distribution, we're just looking for the first success. So which would imply that the observations that come before said first success are all failures, which is why we have this 1 minus p portion of the function there. Now, the mean, the expected value here, so the mu of y is just going to be 1 over p. And remember, we use either mu or the expectation to indicate the mean. And then our standard deviation, which will look like this, the sigma of y, is going to have square root of 1 minus p over p. Now, there are some very wonderful calculus proofs that I will spare you all, but for this proof here. But for the mean, I did want to mention, since we have successes pth percent of the time, and we're looking for the expectation that one success will occur, the reason we have 1 over p, because if this occurs p amounts of time, well, 1 divided by that will give us the total. So for example, if we know that the probability of success is 1/10, well, then eventually after 10 trials here, 10 times 1/10 would give us 1. We'd expect 1 success by then. So that's a little bit of where this formula comes from. And then lastly, notice that we don't start at 0 here. So when we look at the shape of a geometric distribution, it looks something like this. So perhaps at 1, 2, dot, 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 all the way over to k. So perhaps from 1 we have some success here, and then 2 we have some success, and then 3, and then 4, and then 5, and dot, 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 dot. We just keep going until we have that first success. Well, looking at this distribution here, looking at the shape, we are going to notice that we appear skewed right, whether that's relatively skewed right or strongly skewed right. In a geometric distribution, since we're going to go until the first success occurs, we'll notice that a majority of the bulk of the data will be less than the median, and then the rest of the data trails off until we get to that first success. Depending on our sample space, and actually all sample spaces for a geometric distribution, it must add to 1. So we can, we'll do a StatsMetric activity that will help us look at the sample spaces. But essentially, when we look at a geometric distribution, since the probability of success occurs somewhere over here, we're going to have this right-hand tail. And you'll notice that the probabilities do get smaller the more dragged on these trials exist.